Alright, welcome everyone. My name is Dwight Duffie, and in this tutorial we're going to be reviewing the basics of binary. Specifically, we're going to be looking at binary data representation, or how a computer can represent a numeric value in a binary form. It sounds complicated, it looks intimidating, but let me assure you it's easy, it's, as Spock would say, it's logical. Not anything to be intimidated by. I think mostly it's just because it's a different way of thinking and a different way of representing data than we're used to. I teach a computer science for kids class, and I teach kids 6 and 7 years old how to count in binary. It isn't something any harder than learning to count in decimal. It's just a different way of counting, and so for that reason it can be a little bit intimidating. So let's go back and review just for a second. Base 10, which means that there are 10 symbols that we use, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's a system that we're all used to. And if I were to offer to pay you 3, 2, 6, 8 dollars, that would be a nice chunk of change. And we would know that this is the ones, and this is the tens, and this is the 100s, and this is the thousands. And I think just about everyone would know that this is 3,000, 200s, 6 tens, and 8 ones. And we notice that each column is simply a multiple of 10. And that's what base 10 is 10 symbols where in each column is 10 times bigger than the preceding column as we move from left to right. Okay, so if we say that binary is base 2, the reason we say base 2 is because there are only 2 states, and we represent those 2 states as 0 and 1. Now we know that it's not actually a 0 and a 1 that makes the computer work. It's a high and a low voltage that we represent as a 0 and a 1, or it's a negative and positive charge that we store on the disk, or it's an intensity of light, or that's either there or not there, or in some form, or it's a radio frequency. And the bits can move through the network and be stored, and most importantly be processed in an electrical form, which is something that we'll look at in a future tutorial. So let's look at this idea of 8 bits. 8 bits make up a byte, and we could have 8 bits, or we could have 16 bits, or 24 bits, or 32 bits. Obviously the more bits we have, the more bigger number we can represent. It's sort of like the idea that, in general, a 6-figure income is, better than a 5-figure income, and, 7 digits is better than 6 digits. Obviously, each digit gives us 10 times as much. So if we want to calculate the decimal equivalent of some binary value, let's say 0, 0, 0, 0, 0, 0, 1, 1, and I think I'm going to make this 1, 1, 1, 1. I think that's a good starting value. We want to come up with what is the decimal equivalent for 0, 0, 0, 0, 1, 1, 1. And we'll double check. We've got 8 bits here. And the way we do it is we have a decimal equivalent column heading, and we start with the number 1, just like we do with decimal, just like we did with base 10. But instead of multiplying by 10, because it's base 2, we multiply by 2. So we'll have 2, because 1 times 2 is 2, and then 2 times 2 is 4, and then 8, then 16, 32, 64, and 128. And let me do something a little different with the font on this. Okay, so there we have our decimal equivalent for the, the 8 bits that we're trying to represent. So we simply, wherever there's a 1, that bit is considered to be on, so we would add up 4 plus 2 plus 1, because those are the on bits. So 4 plus 2 plus 1 is, if we add those up, that gives us the number 7. So if I have 0, 0, 0, 1, 0, 1, 0, 0, 1, then I'm simply going to say 16 plus 4 plus 1, because it's the 16-bit column is switched on, the 4 and the 1. So 16 plus 4 is 20, plus 1 is 21. So that's the way the computer would represent the number 21. So if you had 21 in a spreadsheet, the computer would represent it. If it was an 8-bit number, it would represent it as 000100101. If I have all ones, it's probably easiest just to memorize that that's 255. And if we added up 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, it would be 255. And if we know that, if I have all ones, but let's say I switch a couple of these to zeros, I'm subtracting or turning off a 4 and a 1. So if I subtract a 4 and a 1 from 255, what would I get? I'd get 250. Now another interesting little trick that you can do when solving these problems that's sometimes helpful when you're dealing with, a string of ones, is to recognize that 4 plus 2 plus 1 is 7, and 7 is 1 less than 8. So any string of binary bits is 1 less than the next column. So if you double 128, it's 256. 1 less than 256 is 255. So if I were to ask you what's 1, 1, 1, 1, 1 in decimal, I could just say, okay, 1 less than the next bit, which is 1 less than 32, that would be 31. You wouldn't have to do that trick. You could just add up 16 plus 8 plus 4 plus 2 plus 1, but it will always work out, because we're doubling in each column, that the sum of the preceding columns will always be 1 less than the next column. Okay, so I'm going to go ahead and copy my little cheat sheet here to my next page. I don't know if this is going to paste in. Yucky. There we go. So if I want to calculate the opposite direction, meaning from decimal back to binary, and I have a number, 7, then the technique for doing that is to go from left to right. And do I need 128? No. Do I need 64? No. 32? No. 16? No. 8? No. And then based on our little rule, we know that I need a 4. And I need to pause this for a minute. Hello? All right, sorry about that. So picking up where we left off, we're moving across from the left side to the right side, and we need a 4, yes. Now we're at 4, we need a 2, so we'll go ahead and turn that bit on. Now we're at 6, and we need a 1, and that equals the 7. Because each column is half of the preceding column, and we end with a 1, we'll always end up with exactly what we need if we do this problem solving from left to right. So if I wanted, for example, to pick up the value, say 62, which is going to be a little bit harder one. Do I need a 128? No. Do I need a 64? No, because that would be like busting in blackjack, or going over the number and the price is right. You don't want to go over. Do I need 32? Yes. And if you don't grab the 32, remember the sum of all the rest of the bits is 31, and you'll never make it up. So you've got to take it as you move from left to right when you can. So I need a 32. And then if I move over to 16 and turn that on, now I'm at 48. 32 and 16 is 48. And then I'm going to be at another 48, and I should be at 56, and then 4 I'm at 60, and then at 2 I'm at 62. And if I turn the last bit on, I'd be at 63, which is 1 less than 64. All right, and I can pretty much I can string out and add additional bits if I want to go to 16 bits or 24 bits or 32 bits or 64 bits. The numbers get progressively larger where each column is doubled. All right, so we'll pick an easy one. How about 22? So do I need 128? No, no, no. 16? Yeah, I better take the 16. Now, if I took the 8, I'd be at 24, so that's too big. So I'm at 16, and I might make a little mental note that I need 4, 5, I need 6 more. So 8's too big. Do I need the 4? Yep, better grab it. Yep. Do I need the 2? Yep. Do I need the 1? No. And then just go back and double check. 16 plus 4 is 20, plus 2 is 22. All right, so that's the basic of binary problem solving. If we want to actually count in binary based on what we just learned here, let's just do 3 bits. 0, 0, 0. We can make it bigger than that. Come on. All right, here we go. 0, 0, 0, of course, is a 0. And then the next number would be 0, 0, 1, because that's a 1 in the 1's column. And then we'd go 0, 1, 0, because that's the 2's column. And then 3 would be 0, 1, 1. 4 would be, that's 3. 4 would be the 4 column, and then 0, 0. And 5 would be 1, 0, 1. 6 would be 1, 1, 0. And we could continue on, and we'd go all the way to 7. I guess we might as well just finish this up. And then 7 would be 1, 1, 1. And then we would just double check. Do we have 8 values? 1, 2, 3, 4, 5, 6, 7, 8. So we start at 0, and then we end up at, in this case, 7. All right, so just taking a quick look at the binary worksheet here. I guess we just did the answer for that. 0, 0, 0, 0, 0, 1, 0, 1, 0. Okay, I think that's enough for that one. How many possible combinations in 1 bit? It can either be on or off, so it would be 2, and then 2 bits we double would be 4. Right? And then 3 bits would be 8 possible combinations. Okay, I think that's enough for that. If we're going to convert these values, we already know what this is, right? This is 7. This would be, we'd have to go back to our little chart, but this is the 1s, the 2s, the 4s, the 8s, and the 16. So we can do that, and then here again we would do the problem solving the other way. We'd say 0, 0, 0, 0, 0, 1, 1, 1, and that would be our binary for 7. 12 would be 0, 0, 0, and then we'd need the 8's column on, and then we need a 4, and we'd need the 4 columns, no 2, no 1. So 1 and 1, 0, 0 would be the answer for 12. Okay, so should be easy to complete the binary worksheet if you're required to do one. That'll conclude this tutorial.